Good evening, everyone. Myself, Anshul Singh Thakur. I'll be your TA for this course offered by Professor Bhim Singh sir from IIT Delhi. This is our 10th session, and I am a PhD student at ICER department at IIC Bangalore. And as I mentioned, this is our 10th session. So we'll be discussing the content of week 10 offered on your course. And as we usually go, we'll start with the theory discussion of the topics that have been covered in the past weeks related to the assignment questions. Like the assignment questions to be submitted on 12th are based on hybrid power filters. So in this lecture, we'll be discussing first, we'll be revising the content of the lectures that were discussed by Bhim Singh sir in his lectures. And then we'll go ahead with solution of the numerical problems in order to understand those concepts better. Okay, so let us get started. If you have any doubts right now, you can ask me, or and in case you have any doubts in between the session, then also please feel free to ask any questions. Okay, so far we'll start by just revising what we have been going doing so far. So far we have been discussing about power quality, right? So power quality has lot of aspects. So we started by discussing basic definitions of power quality. Now, after discussing what is power quality and we studied the definitions and the need for power quality improvement. Then, since we defined a problem that there is a problem of power quality and we need to solve it. So, in order to solve this problem, we started discussing the solutions that are present in this area for improvement of power quality. So, when you talk about the solutions for power quality improvement, they are broadly categorized into two major categories. One is passive kind of compensation, and another one is active kind of compensation. So, when you talk about passive compensation means the compensators that are made up of R, L, and C elements, passive elements, whereas active compensators are made up of R, L, and C elements along with switches. So this is the only difference between active and passive compensators. So we started by discussing a lot of power quality problems due to nonlinear load. So there are current type of power quality problems, and then there are voltage type of power quality problems. So one by one we started discussing power quality problems. So fewer based, broadly they can be categorized into current based power quality problems and voltage based power quality problems. Then we know that in order to take care of current based power quality problems, we could again go for passive kind of compensation or active kind of compensation. So an example of passive compensator is a shunt connected capacitor, or an example of an active is a D-STATCOM. Because D-STATCOM is connected in shunt with our system, and this D-STATCOM is taking care of the current based power quality problems. Similarly, for voltage based power quality problems, we can have again the same classification, passive and active. And when we talk about the passive nature of these voltage based power quality problems, we could think of a simple inductive filter. And for active compensation for voltage, we have discussed about DVR, right? Dynamic voltage restorer. And when you want to take care of both current and voltage based power quality problems, then you have an example of UPQC, Unified Power Quality Conditioner. So in this UPQC, you were able to take care of both current and voltage based power quality problems. So far we have been discussing these lot of solutions, and a part of so far we were taking care of, we were keeping passive, we were first discussing the passive kind of compensation, and then we were moving on to active kind of compensation. But we haven't studied both of them together. What if I can use a combination of passive and active? Why not? So this is one type of solution, and this type of solution is called hybrid kind of compensation. So in this week, we in in this today's lecture, we'll be discussing about these hybrid type of compensators. So they have a combination of both passive and active components. They could either have both series and shunt active filter, or they could have a series and shunt passive filter, or a combination. Okay, so all these hybrids come in this category. There are a lot of combination. There are a lot of combination possible in this particular type of filter. Okay, so we'll be discussing these in today's lecture. And apart from that, we in the theory course or in the module course that we have been discussing, we started with discussion of compensators, both passive and active compensators, and then we started discussing about filters, passive and active filters. So there is no big difference between them. The only reason we studied them separately is because while we were discussing about compensators, we talked about reactive power compensation and unity power factor operation and voltage regulation. Whereas when we started discussing about filters, we focused on harmonics. So the only reason we studied both of these compensators and filters differently is in order to simplify our understanding. But in practical conditions, you can have a compensator which can perform all these functions together. Okay, so in practical situation, you need not have to segregate them and study, but only for the sake of your understanding, we have segregated and studied it. Okay, so we'll move on to the discussion for today in today's lecture, that is hybrid power filters. Okay, so as we know that there are two types of major power quality problems. One is voltage based power quality problems, another is current based power quality problems. So far in the previous lectures that we have been discussing, we talked about tackling just the voltage power quality problem or the current power quality problem. Now in this lecture we'll be focusing on a system which has both current and voltage based power quality problem. So we are focusing on a system that has both current and voltage based power quality problem. So this is our target system for this particular lecture. Okay. Now now what happens due to the presence of these voltage and current power quality problems? What happens in our distribution system? The RMS supply current increases. Why? Because of the presence of harmonic current. Then there are increased losses in the system. Then there is because of the increased losses, there is poor power factor. Because of all these problems, we are unable to utilize the existing infrastructure to its full capacity. Suppose my grid line has a rating of 20 ampere, which is IRMS. But because of the presence of harmonics, my let us say I am able to supply only 10 ampere current, and rest 10 ampere current is going just to compensate the harmonics, and that is just the RMS of the harmonic component that is present. So effectively I am able to utilize only half of the rating of my line, right? Because in reality I have 20 ampere as maximum rating, but due to the presence of these harmonic currents, I am able to pass only 10 ampere of active current, RMS current, because of which I am able to utilize my grid to half of its capability. This is what this point is telling us. Then, because of the losses, as we mentioned, there is losses, huge amount of losses in the harmonics. So, losses in any kind of grid are I square. If you say I square R losses, then since the RMS current or the harmonic current increases, then I square R losses also increases. And because of these losses, heating takes place in the components of the distribution system. And because of that, we have to derate the distribution system. We have discussed derating before also, so we will discuss just revise it one more time. So, derating means we have to derate this 20 ampere line to 10 ampere line just because we need to give 10 ampere space for harmonic current to flow. So in order to tell it to my subordinates that this is a 20 ampere RMS line, I will tell them that you can pass only 10 ampere active current through this line. That means I am derating this line. Why I am derating? Because of the presence of these harmonic components and losses in the system. Okay. Then, then other power quality problems in the system are distortion in voltage waveforms at point of common coupling. Why does distortion in voltage waveform happen? So let us say I have a synchronous generator which is giving me beautiful sine wave, but I have a load connected far from this place, and this is my load. So this transmission line will definitely have some certain amount of source impedance, right? And because of the presence of the source impedance, what will happen is there will be a voltage drop. And if I say that the load current that I'm consuming is non-linear in nature, then what will happen is VL. So VL is equals to Vs minus IL into Zs, right? And this IL is non-linear. Therefore, this VL will also become non-linear in nature. Therefore, we say that distortion in voltage waveform occurs at this point of common coupling. This is the problem here. And because of these high frequency components or high frequency noises, interference occurs in the communication system. And what happens is if I am the one who has a bad load or non-linear kind of load, if this is me and there is my neighbor here, this is my neighbor, okay. But since I am drawing non-linear current and this VL is now non-linear in nature, my neighbor is also getting non-linear voltage, which is a very big problem because I am the one who is running a non-linear load in my home, and because of my non-linear load, my neighbor is suffering now. So that is one of the major reasons of conflict between people when we talk about power quality. That is, and the long-term impact of these, you will say that nowadays in our homes, what we do is we just focus on whether electricity is there or not. If electricity is there in our home, we are happy. But is that the way to go? No. So what happens in the long run when we have low quality of power supply in our homes? The life of the electrical equipments which are connected to the load are is is reduced. If this is my source and this is a bad quality source and this is my load, then the life of this load, if it was supposed to be 10 years by default, then because of the poor quality supply that I'm giving to this load, it might reduce to just 5 years. That is a problem in these scenarios. Okay. So a single one-stop solution for all these kind of problems is hybrid power filter. Hybrid power filter is like Ramban we call it, right? A one-stop solution for all the problems. You just have to put this filter. Although if you talk cost-wise, will this be a cost-effective solution? That might not be. So that is a different discussion. But if you want to just put a single solution to any kind of power quality problem, be it current or voltage, you can directly put a hybrid power quality, high hybrid power filter if cost is not a constraint for you. Okay. And this hybrid power filter is a combination of both. It could be both shunt and series filter. This shunt component could be passive or active. Then this series component also could be active or passive. So whichever combination is present, that will come in the category of hybrid power filters. Okay. Now let us discuss the state of the art of on hybrid power filters. So currently, if you look in the market in the category of hybrid power filters, the hybrid power filters are able to provide us harmonic elimination. They are able to give us reactive power compensation along with load balancing. They are able to compensate the neutral current in the three-phase four-wire system. Then they are also the series part of these filters are able to take care of voltage, supply voltage. They are able to maintain beautiful sine wave voltage for the loads which are very sensitive to the voltages. Then they are able to take care of harmonics, sag and swell, surges, spikes, notches, unbalance, etc. So all these problems are taken care by just one equipment that is called hybrid power filters. So that is the reason of their popularity. Now, when we talk about the classification of hybrid power filters, as we have been discussing for almost all type of filters, there is this standard. There are standard three bases of classification. First is on the basis of type of converter. Second is on the basis of the topology configurations involved. Then third is based on the supply system. So when you talk about the converter type, so we have discussed there are two types of converter. One is current source converter, another one is voltage source converter. Now, whether we are using a voltage source converter or a current source converter uh, in our UPFC or in our hybrid power filter, that defines the one of the basis of classification. And we have been discussing from various lectures that voltage source converter is much more preferable over current source converter because of certain reasons, and few of those reasons are since the switches present in voltage source converters have lesser losses, they are widely available. The size of the capacitor that is present in voltage source converter is much smaller, and the cost is lesser compared to an equivalent inductor that is placed in a current source converter. So all these are the reasons why we prefer voltage source converter over current source converter. So even in the rest of the topologies that are going to follow, we will be using voltage source converter in our topologies. Now, another classification is based on the topology of these configurations. Now, after finalizing whether I'm going to take a current source converter or voltage source converter, suppose decided on taking a voltage source converter. Now, in voltage source converters, there are n number of options for topologies. There is half bridge, full bridge, three leg, four leg, three leg with split capacitor, lot. These are just the few popular topologies. If you go in the literature, there are, you can call it infinite as well. There are n number of topologies that you can pick. So based on those topology that you select there, you get this basis for classification. Okay. Then there is third classification, which is based on the supply system. Now, the supply system to our homes could be a two-wire system, three-wire system, or a four-wire system. So, based on this classification, whether we are talking about a compensator or a power filter for a two-wire supply system, or three-wire supply system, or four-wire supply system, we can categorize our filters in these particular three categories on the basis of their supply systems. So if you look at the hybrid filter, there could be single phase, three phase three wire, or three phase four wire. And all these three can be categorized into either passive passive. Passive passive means passive in series and passive in shunt. Then passive active is passive in series and active in shunt. Active active is active in series and active in shunt. And all these three combinations are available for all the three different supply systems. Okay, so these are just the few examples. When you talk about passive passive, it could either be RLC in series or RL or LC in parallel. There are n number of combinations available. Okay, so don't get overwhelmed if you look at the lot of topologies present for hybrid filters. You just have to stick to the basic principle of what function does a hybrid filter perform, and just by looking at that basic principle of hybrid filter, you will be able to understand what any of those topologies is doing. Okay, so we'll be looking at few of the examples of these hybrid filters. So if you look at this one example, which is made up of passive series and passive shunt filter. This is passive series filter and this is our passive shunt filter. This is the most popular topology that is used in many places. Then another alternative to this is I could put this series filter this side and passive filter this side, right? This is another combination possible. But this is less popular because most of the loads that we have are of current fed type of loads or voltage fed type of loads. Okay, so because of those nature of loads, this is the most popular topology available. And another advantage of hybrid filters is that when you talk about shunt filters, they have a problem of having resonance issues. So when these shunt filters can be a part of resonance problem when you just use a shunt filter. But when you use this passive shunt filter along with the series filter, in case the resonance occurs, this series filter blocks the resonance current, the current due to resonance. And because of that, the series filter is able to take care of the drawback of the shunt filter. Similarly, our series filters have a drawback of voltage drop across it. Suppose as a part of series filter, I have an inductor. Then during the fundamental frequency operation, that inductor is unnecessarily giving me a drop. I cannot short circuit the inductor during some time and then again bring it in the circuit. It will be connected all the time in series. And because of that connection at fundamental frequency, I will have an unnecessary drop across the series filter. And this drop can be taken care by the capacitor which is present in the shunt. This capacitor can take care of the voltage drop that is occurring due to the presence of this series filter. So we can again say that the drawback of series filter are handled by shunt filter. So that is so because of these two features that we just discussed, hybrid filters are becoming much more popular. I'll repeat one more time. What happens in hybrid filters is that the series filter takes care of the drawback of shunt filter, and shunt filter takes care of the drawback of series filter. And because of that combination, they both together form a very good combination which have very fewer drawbacks. So that is the reason behind the popularity of hybrid filters. And what is the drawback of series filter? The drawback of series filter is that it is having a drop across it during fundamental frequency operation, and the drawback of shunt filter is that it may lead to a problem of resonance, and this problem is solved by series filter by blocking that resonance current. Okay. So as we discussed this one topology, then second topology is just the opposite. We have shifted the shunt here and series here. That gives rise to the second topology. Then there could be passive again. There could be a T network, that is passive series, passive shunt, and then passive series again. And then using these three again, we could have this pi network where there could be passive shunt, passive series, and passive shunt again. There are, as I mentioned, there are n number of topologies that are available. So you can never have, hold of all the topologies. Just stick to the basic principle behind these hybrid filters, and then based on that basic principle, you will be able to understand or design any of the topologies that you want. Okay. So now, if you look at this, so this is a these are examples of passive active combination. So the one and two, 1, 2, 3, and 4 were the example of passive, right? Because only passive filters were involved here. But when you look at these topologies, they have a combination of both passive and active. So if you look in this topology number one, it has a combination of both passive series and active series. Or you could have these passive series and active series in parallel. These both comes in the category of passive active. Similarly, you could have shunt active and series passive, or you could have shunt active and shunt passive, or you could have a parallel combination of shunt passive and shunt active. So there are n number of combinations that are possible. You can never have the complete analysis or the list of all these. Any kind of combination that involves a passive filter along with active filter, or a combination of multiple passive filters or multiple active filters, is called as hybrid filter. Okay, these are a lot of topologies that were discussed in the class. You could just go through the diagram in order to get an idea of what kind of topologies you could come across while talking about hybrid filters. Okay, the basic principle is always the same. They will have an active component or a passive component. So the basic principle will always stay the same. Okay. Now let us discuss the principle of operation of hybrid power filters. So when you talk about the principle of operation of these power filters, the main objective of hybrid power filters is to mitigate multiple power quality problems, which are based on both current and voltage. So we need to tackle both voltage and current based power quality problems using the hybrid power filters. Now, these hybrid power filters mitigate most of the power quality problems for satisfactory operation of the consumer equipment. So, we have studied before UPQC, right? UPQC also takes care of both current and voltage based power quality problems. But the difference between UPQC and these hybrid filters is that while doing the design or the analysis of UPQC, we considered that the supply system has sinusoidal voltages, and or we did not consider the non-idealities that were present in the supply system while discussing UPQC. Whereas while discussing this hybrid power filters, we'll be talking a lot about non-idealities in the voltage or the supply system as well. So that is the difference between hybrid power filter and UPQC analysis. Okay, the basic principle is not very different. You will use the equations and the principles that you have studied for UPQC, but the only major difference here in this analysis will be that we'll be taking care of the voltage non-idealities as well in the system. Okay, and what will be the result of putting hybrid power filters? When we put a hybrid power filter into a system, our supply current will become sinusoidal in nature, irrespective of the nature of load current. Okay, this is the observation point in all the waveforms that you will obtain. So when you take this topology number one as an example of an hybrid power filter, which has both passive filters, passive series filter and passive shunt filter. So if you look at this particular diagram, so these passive and shunt passive series and shunt power filter together form what we call as hybrid power filter, and they take care of harmonic compensation in both voltage and current. These passive shunt filters suffers from inherent problem of series and parallel resonance alone, whereas and similarly series filters suffer from the problem of voltage drop when they are just put alone. But together they form a robust combination, as we have just discussed above, right? Hybrid passive power filters provide harmonic compensation at par with active filters, which design is insensitive to source impedance and eliminates the chances of resonance over wide spectra and reduces large variation of power factor and terminal voltage with by varying such rectifier type of nonlinear loads. Similarly, another configuration, if you look at, this is a combination of both passive and active. So here what is happening is you are connecting shunt passive filters, and then in the series of the shunt branch you have active filters. So the sizing of this active filters is 5 to 10% of the overall size. So the advantage here is that if you put if you replace all of this with just one active filter, then the cost will be very high. So in order to reduce that cost, what we are doing is we are asking the passive compensators to perform 95% of our function at a lower cost, and then the rest 5% of the function is performed by this active filter. So using the active filter, we are able to give a degree of flexibility to our system, and also we are able to reduce the cost of the system by reducing the sizing of the active filter. This is the advantage of this particular topology. So the passive filter suppresses harmonic current produced by the load, whereas the active filter improves the filtering characteristics of the passive filter. So what happens here is we know that for passive filters to work properly, we know that at point of common coupling, the voltage should have harmonics. Because until there are harmonics in the voltage at point of common coupling, there will be no harmonic current at this point that can go through the passive branch. So in order to maintain harmonic voltage at this point of common coupling, we can use these series filters. And using these series filters, we will make the point of common coupling voltage harmonic in nature so that all the harmonic current flows through the passive filters, and the load and the supply has to supply only sinusoidal currents that we will be seeing in the performance tab. In the next few headings we'll be able to see the waveforms. Okay, so until then you can just imagine that the nature of sinusoidal currents will become sinusoidal after application of hybrid power filters. Now, by actively improving the compensation characteristics of the tuned passive filters, the need for precise tuning of the passive filters is avoided, and the design of the passive filter becomes insensitive to supply impedance up to some extent. Then there is another principle of operation of active series and passive shunt based hybrid power filters. So in this particular topology, there is active series and passive shunt. So this is also a very popular kind of topology that is being used. The major rating of this compensator is is due to the presence of passive shunt filter, and the minor part of this compensator is due to the presence of active series filter. So the active series and passive shunt based hybrid power filter provides a cost effective solution. So this particular topology where we have an active series compensator and a passive shunt compensator, they together perform a very cost effective, and they give a very practical solution for the harmonic solution. for the harmonic compensation. So the again the advantage of this topology is similar to the advantage of our previous topology. In both the topologies, our advantage is that due to the presence of passive components, the cost or the sizing of the active filter is reduced, and because of that, the overall cost of this hybrid filter is less than the system where we would have just put a active whole active filter. So that complete if I compare the this particular problem solution with a full active compensator compared to active plus passive, then this active plus passive is a much more cost effective solution. So again, the rating of this active filter is less than 5% of the overall rating of the system. The passive filter suppresses harmonic currents produced by the load, whereas active filter improves the filtering characteristics. Again, the same logic. Because we know that in order for these shunt passive filters to work properly, we want the voltage at the point of common coupling to have harmonic components. And in order to make that voltage have harmonic components, these series filters will play a very big role. Okay. So the series connected active filter is controlled to act as a harmonic compensator for the load by constraining all the harmonic currents to sink into the passive filters. And this eliminates, and due to the presence of the series active filter, we are able to eliminate the possibility of series and parallel resonance in the shunt passive compensators. Then there is another topology. So this is an active-active topology. In this topology, both active series and active shunt compensators are present. So this compensator I am using for active series purpose, and this compensator I am using in shunt. So again, this is called a universal active power filter because both the series or the shunt part are active in nature. Therefore, this is called universal active power filter. This has two voltage converters. One voltage source converter is will help in the series, and another voltage source converter will be connected in shunt. Both the voltage source converters use PWM control, and both of them use standard. The hardware will be almost same as what we have been discussing so far. We will use Hall effect voltage and current sensors for sensing part. We'll use a DSP board for implementing the control algorithms that we have been discussing so far, and we'll be implementing these control algorithms in the DSP boards, and solid state devices will be used. So for the series VSC, if we talk, that series VSC is called AFSS, that is active filter in series. We will be denoting it by this for representation. And the shunt filter is called active filter in shunt, just for the purpose of our understanding. Okay. This series voltage source converter. So in the series part, we'll be using PWM or the pulse width modulation in voltage control mode, because in series we want to control the voltage parameter. Whereas the shunt voltage source converter or the active shunt filter, in this filter, we will be using pulse width modulation and current control mode. Because when we are connecting in shunt, we want to control the current that is flowing into the system or at the point of common coupling. Therefore, this universal active power filter is considered as a perfect solution for the elimination of both voltage harmonics and current harmonics. So if you have any doubt regarding what kind of system you want to put and you have a lot of money and there is no constraint, by default you can just put universal active power filter there. It will take care of both voltage and current based power quality problems. So currently we are focusing on current harmonics and voltage harmonics. These are only just two current and voltage related power quality problems. If you want to take care of more voltage power quality problem or current power quality problem, like you want to take care of reactive power compensation and you want to take care of voltage fluctuations or voltage notching, all these things can be taken care by this particular hybrid filter. Only change that will occur is the rating will increase. So, like we have been discussing in few numerical problems, we discussed finding the rating of the compensator for just reactive power compensation and just harmonic compensation. And then in the third case, we found out the rating of the compensator for both reactive power compensation and harmonic compensation. So so depending on what goal I want to achieve using my compensator, my rating of the compensator will vary. and that is the only constraint in my system. Because if the rating increases, the cost increases. Apart from that, most of the there are generic configurations available that can perform a lot of functions. But just for the sake of cost, in order to save cost, we settle for fixed compensation or just capacitors or just inductors. So when there is only one problem, why to put a solution? Like we say that we don't use a pin in place of a sword, or vice versa. So if problem is being solved by using just a pin, why to use a sword there? This is like a sword, okay? And if the problem is very small, or it's just a single power quality problem, we just try to solve it using a fixed kind of compensation instead of putting this sword or the hybrid power filter or universal power filter over there. So depending on application, you have to choose wisely which kind of filter will be more cost effective and will serve the purpose and is more utilized. If I put this filter just at a place where only voltage has to be maintained or power factor is to be corrected, this is a very overkill solution. So while giving a solution, you need to take care of these aspects as well. Now let us look at the analysis and design of the hybrid power filter. So when you look at the analysis and design of these particular topologies of hybrid power filters, let us pick this particular topology where there is a shunt passive filter, and then in the shunt there is a series active filter connected. So if I am asked to design this filter, what all things will I have to take care of? So since considered configuration of hybrid filter consists of passive filter along with a small active filter, therefore it consists of both passive and active component. Now let us assume that in the design procedure, I am assuming that I have a three-phase system with 415 voltage, 50 hertz supply system, and the load that is connected, this nonlinear load, is a 25 kilowatt resistive load. Now, if I look at the design of the passive filter first, then the passive filter is just a series combination of inductor and capacitor tuned at particular frequency. Now, since this is a three-phase system, I'll be designing for fifth and seventh harmonic, right? And then for fifth harmonic, I'll be using a series tuned filter, and for the seventh order harmonic, I'll use a high pass filter. Then, in order to consider the design procedure of the series tuned passive filter, is explained for voltage fed type of load. If you look at the design procedure for this particular rating 25 kilowatt of load, we know that first of all we start by calculating the reactive power requirement of our system. Then once you obtain the reactive power requirement, from that reactive power requirement, we calculate the capacitor sizing by assuming that identical capacitors are placed in all the branches. After finding out the value of capacitor, using the formula for the frequency of LC filter, omega is equals to 1 by root LC and omega is equals to 1 by under root of LC. Using this formula, we find the inductance value. And then after finding the inductance value, using the quality factor, we find the value of the resistance that will be put in the that will be put in the filter. And this quality factor depends on what kind of filter we are trying to design. When we are trying to design a particular nth order tuned filter, then we take the quality factor to be in the range of 30 to 100. Whereas when we design a high second order high pass filter, then we put the Q in the range of 0.5 to 5. Okay, so that we have already discussed. We were just revising that again. Then, now when we come to the active series filter part, while designing the active series filter part, we know that the rating of this filter is only 5% of the load rating. And using this sizing, we can design the whole filter using the same procedure we have used for designing of active series filter. So you can use the same design procedure. Okay. In addition, there are several numerical examples that we'll be discussing ahead in order to make this clear. Okay. Then if you want to take care of the design of the active shunt filter, again, we'll use the same procedure that we have been discussing for design of individual active shunt filter. So we have so far looked at the design of active shunt filter, passive series filter, active series filter. Individually, we have looked at their designs, right? So just on the basis of those designs, or the same lectures, you can just follow the same design procedure. And don't worry, we'll be looking at the design in the coming numerical problems so that you get the hang of how to handle such a big problem at once. Okay. Then if you look at the control of hybrid power filters, then we have been discussing that since these active filters have switches, and these switches need gating pulses. And in order to obtain the gating pulses for these switches, we need to use certain kind of algorithm in order to generate the reference currents for our switches. And then based on those reference currents, we'll be able to obtain the gate pulses for these switches. Now, what kind of control algorithms shall we use for hybrid power filter? So in today's lecture, we'll be discussing just two of the very basic algorithms. But in literature, there are a lot of algorithms that are available that you can use. Okay, so you just have to focus on the uh, basic principle behind these, and what should be the input, what can be the input of these algorithms, and what should be the output of these algorithms. Just focus on that. The change in from one algorithm to another, while moving from one algorithm to another, the only change that occurs is in the basic principle involved in the algorithm. Only the basics on how the reference current is generated that changes. Apart from that, the input and the output almost remains the same. Okay. So if we consider this particular system of parallel hybrid power filters, where where these passive filters are connected in shunt, and then active filter is connected in series with that shunt branch. Let us consider this particular case. So the main objective of control algorithm is to estimate the reference voltage and currents. So after estimating the reference voltage and current, we'll be able to obtain the gating pulses, right? We have been looking at these control algorithms for quite some time now, and we know that. And so the main goal of these control algorithms is to generate reference voltage and current waveforms. And there are a lot of control algorithms available that I have just told you. We have discussed the classification also of these control algorithms. Broadly, they are classified in the category of time domain and frequency domain algorithms. So based on that classification, we can easily analyze, we can easily understand or classify these algorithms that are present all over the literature, and we can understand them. Let us look at one example of control algorithm of hybrid filter, which is based on instantaneous reactive power theory. So if you look at this diagram, what is happening here is we are first of all sensing the supply voltages VSA, VSB, and VSC. And also we are sensing the supply currents ISA, ISB, and ISC. Then using the cloud transformation, we are transforming these ABC voltages into alpha beta domain. After transforming these supply voltages and currents into their respective alpha beta domains, using these alpha beta domain parameters, we are able to calculate the active and the reactive power, instantaneous value of active and reactive power. And this is the standard formula. Now, we know that these are instantaneous values, and these instantaneous value will have both DC and AC components. So when I pass these signals through high pass filter, I am able to obtain the AC part of the signal, and the DC part is filtered. I want only the varying part. I don't want the fixed part. So after filtering, I obtain the AC part, and this AC part of active power becomes my reference active power. Similarly, for Q star, I need some reactive power in order to maintain the DC link voltage equivalent to the reference voltage. So we have discussed this before also, right? So whenever there is a compensator and there are some losses, it's not an ideal system, right? The switches have losses, certain active power losses takes place in that converter, and as a result of active power loss in that converter, the DC link voltage reduces in magnitude. And in order for the proper functioning of this compensator, we need to maintain a fixed DC link voltage. So in order to maintain that DC link voltage fixed, we have added this additional loop here where we try to maintain the reference DC voltage as VDC star. And in order to maintain that, we will sense the DC voltage. Then we'll find the average value of the DC voltage because it will have oscillating components as well. So we'll compare it with VDC reference. then we'll pass it through a PI controller, and then we'll generate this output. And after adding that to the reactive power reference, we'll be able to obtain the Q star. Then using this particular equation, from PQ star, we can obtain I shunt A star, I shunt B star, and I shunt C star. So after obtaining these references, by multiplying them with the respective particular gain, some gain K, I can obtain the reference voltages. And then from these reference voltages, I can obtain the gating pulses that will be given to my active compensator, this active compensator. The gative pulses that are present here will be given to the switches present in this active filter. Okay, so this is how we use this particular control algorithm. Now, if you look at the equations of these particular control algorithm, then you know that using the ABC phase voltages, you will first obtain the alpha beta parameters using the Clark transformation. Similarly, from sensed ABC supply currents, you will obtain the supply alpha beta parameters. Then using Vs alpha, Vs beta, Is alpha, Is beta, you calculate the P, Ps and Qs values, which will have both DC and AC components. Then from these, I need the AC components, and in order to obtain that, I put a high pass filter that will just give me this AC component, PS tilde and QS tilde. After obtaining these AC components, I put a voltage VDC reference loop, and this is the equation for the PI controller. And using that, I am able to obtain the P star and Q star references. And then once I have obtained these references, I am able to obtain the shunt star currents. And using the some gain K, I am able to convert these reference currents into reference voltages. I'm converting them into reference voltage because because they are series filters, and I told that for series filters I'll be using voltage control mode. And for voltage control mode, I need voltage references, right? And then based on this reference voltage, we'll generate the gating pulses, and these gating pulses will be compared with triangular carrier wave. In order these reference VC star will be compared with triangular carrier wave in order to give us the gating pulses. And these gating pulses will be given to the switches of the active series filter. Okay, so this is how this algorithm will work. Now, if you look at another example of another algorithm that is called indirect current control for active element. So in this particular algorithm, what is happening is, first of all, again, this VDC loop, why we are doing this loop will remain same. Why it will remain same? Because in all the, no matter what kind of control algorithm I am using, I have to maintain the DC link voltage to equal to its reference value, that is VDC star. I have to do this because no matter what control algorithm I use, there will be losses in the switches. There will be active power consumption, very small amount, but there will be. And because of that active power consumption, my DC link voltage will drop. And I need to maintain that DC link voltage to a fixed value in order to take care of the proper functioning of my compensator. Therefore, this loop is again similar. So using this loop, I am generating some constant Ki. Now, what I am doing is I am sensing the supply currents and extracting the fundamental component of the supply currents using some algorithm. And after extracting the fundamental components of the supply current, I am multiplying these fundamental components with the constant Ki, and then I am adding these the fundamental component with the prod with the supply currents multiplied by this factor Ki. So using that addition, I am able to obtain the fundamental reference current for the supply current. And using that in a hysteresis current controller, I am able to obtain the gating pulses. Okay, so this is a very simple algorithm, but if you might have heard pi electronics, then you know that the disadvantage of hysteresis control method is that it is a variable frequency method, and since it's a variable frequency method, what happens there is that the sizing of the inductor or the capacitor has to be done in with respect to the worst case scenario. So that is the disadvantage of the system. Apart from that, it's a good algorithm. It is simpler algorithm compared to the conventional control algorithms. So if you look at the mathematics of this equation, we have obtained if you look at the mathematics of this equation, we were able to obtain the alpha and beta components from the ABC components, and then from the ABC components, I was able to obtain the DQ components. Then from the DQ components that I had obtained, I am able to I am extracting the the DC component from this DQ components. So these first I am converting ABC into alpha beta domain, then alpha beta to to DQ domain. Sorry. Then these DQ domain components, I am filtering them using a low pass filter in order to obtain the DC components. And using that DC components, I'm again converting the DC DQ component into alpha beta and then that alpha beta into ABC. And these ABC components will act as a reference current for my system along with another factor Ki multiplied by these currents, and the sum of both will give rise to the supply reference currents. And then using these reference currents, I am able to obtain the gating pulses for my switches that are present in active series filter or any kind of active compensator. These are the two examples, two basic examples of the control algorithms that we have discussed right now. And then let us look at the modeling, simulation, and performance of these hybrid power filters. What will the simulation look like? So if we consider this same hybrid filter, which has passive series and passive shunt compensator present along with a nonlinear load, and this is the design specifications of this hybrid power filter, then if you look at the waveform of this filter, then you will observe that in the duration of 0.02 to 0.06, only series active power filter was working. And then from the duration of 0.06 to 0.12, both a hybrid power filter started working. So if you look at this particular duration, you will see that the supply currents are much more sinusoidal in nature, and there is shunt. The shunt filter also started operating. Initially, shunt filter was not operating because the current is zero, and then the shunt filter started operating. So if these waveforms, since they are of very high magnitude and very the resolution is very low. So if you look at the THD graphs of this, you will be able to understand better. So this is the THD of the supply current. This is the supply current. This is the supply current hybrid filter, and this is supply current with passive filter, with series passive filter on. So initially, in the duration from 0.02 to 0.06, when only series filter was working, the THD of my system was 5.33%. And when both the filters started working, the THD reduced to 2.97%, almost half of the THD. So this is the THD values of the supply current. Then if you look at the THD value of the source voltage, then the THD value of the source voltage reduced to 0.03%, as good as ideal voltage source. Also, the THD values of load voltage is 19.69%, which is the desired voltage by the load. So even though the load voltage is highly, non-linear or harmonic in nature, the source voltage is beautifully sinusoidal because of the presence of these compensators. Similarly, if you look at the load, the THD value of the load current, it is 12.6%, very high. And even after the presence of this highly harmonic load of 12%, we are able to obtain beautiful sinusoidal of 2.9% THD because of the presence of hybrid filter. So another example, if you look at is this is a passive shunt filter which is connected in series with an active series filter. So this series filter is also connected in the shunt branch itself. This is a parallel hybrid filter. In this particular case, if you put these specifications, you'll be able to obtain these waveforms. Now, again, the waveforms are not that clear. At the end, you can just observe from the waveform that the nature of the supply current that you're able to obtain with the help of filter is very beautifully sinusoidal in nature. And if you look at in detail at this THG diagrams, then if you look at the supply current because of the presence of hybrid filter, THD has reduced to 1.5%, even though the load current THD is 27.87%. So normally, if you don't use any kind of hybrid filter, your supply current will also have the THD of 28.87%. But due to the presence of hybrid filter that we are using in our system, we are able to reduce the THD value to 1.5% from 27%, which is very good. And if you look at the source voltage THD value, then it is only 2.7%. Similarly, if you look at another topology, this topology is again a passive shunt filter along with series active filter. This time the series active filter is connected in series with the source instead of the parallel branch. So if you look at the performance in this particular case, again the sinusoidal currents are beautifully balanced and sinusoidal in nature. If you look at the THD values of these waveforms, then you will observe that the supply current waveform is having 1.4% only, and the load current is having 21%. So even though the load current have THD of 21%, we are able to obtain a THD of 1.4%, and the THD of the source voltage waveform is only 0.33%. So again, this is the last example, and in this example, we are considering both active filters, active series and active shunt filters. So if you look at this particular case, again you can see here that in this particular case also, the sinusoidal currents are beautifully balanced in nature. And if you look at the THD values here, then when you observe that the load current THD in this particular case was 80%, and in this, even though the load current THD is 80%, the source current THD is beautifully reduced to 2% only, which is very good. And if you won't have put this, then the source current THD would have been 80%, which is very bad. And if you look at the source voltage THD, it has reduced, it is currently 22%, and the load voltage even though the source has lot of harmonics in itself, the load voltage has only 1.4% THD, because here the source voltage was highly nonlinear in nature. We have introduced a lot of harmonics in the source voltage in this particular case. So even though the source voltage was highly harmonic in nature with 22% THD, the load voltage was beautifully sinusoidal. So that means we were able to take care of both voltage-based power quality problem and current-based power quality problem using this particular topology of active-active compensators as a part of hybrid pass filter. Okay, so after looking at these results, I hope you got an idea of why we have been, discussing about all these kind of filters and what are the advantages of these filters. And hybrid is just a combination of the active and series filters that we have been looking so far. Okay, so now after completing this discussion, if you have any doubts, please feel free to ask right now. Otherwise, we'll move on to the numerical discussion for today. Padmashini ma'am, do you have any doubts? Okay, then we'll move on to the numerical part for today. So this is our 10th numerical session, and we'll be solving numerical problems related to hybrid power filter in today's session. So let us start our discussion. So the first problem that we are going to take care in today's session is related to a single phase voltage source inverter with a square wave AC output. So the AC output is given in the form of a square wave AC output, and the magnitude is 230 volt RMS at 50 hertz, is feeding a critical load of 230 volt 50 hertz 5 kVA at 0.85 lagging power factor. This single phase UPAC, that is Universal Active Power Conditioner, which is consisting of shunt and series active power filters. So both the shunt and series power filters are active in nature, is designed for this critical load. We are supposed to calculate the voltage rating of the shunt element, the current rating of the shunt element, the volt ampere rating of the shunt element, then the voltage rating of the series element, current rating of the series element, and the VA rating of the series element. These are the things that we need to calculate in this particular problem. So let us draw and understand what kind of topology will this look like. So they have given us a square wave inverter which will generate square wave output. So let me assume that this is my square wave inverter which is going to generate a square wave output. So this will have a DC voltage at its input, and from here we'll get a square wave output that will go into our source load system. So let me say that this is my source load system, and I have series filter and shunt filter. So let me say this is my series filter injection transformer, and then shunt can be drawn from anywhere, and this is my load. So let me say this is a lagging load that is given in the question. Let me say that it is a RL load. Okay. So if I draw this as a source load system, this is my RL load which is 5 kVA and 0.85 lagging. Let me say this is my load current IL. This is my source current IS. Then this is the VF. This is the injection transformer for the series for the connection of series filter. And let me say this is my series filter. Let me say that they are sharing a common DC link, and this series filter will be connected like this to the injection transformer, right? So this is our series filter part, and this will have a interfacing inductor also. Then along with that, for the shunt part, let me again have four switches. This is my shunt filter. They will be sharing the DC link. Okay, and this shunt will be connected in shunt to our system. Let us say this is my interface filter. Then one will be connected here, and another will be connected at this point, right? So this is my shunt active filter, and this is series active filter. Let me call it as ISH. I shunt. This is I source. Okay. So after imagining what kind of topology, what this topology would look like, we know that this square wave inverter is giving us. Let us try to imagine what kind of VS will look like. So VS is the voltage across these terminals. So we, since it is given in the question that VS will be a square wave inverter. So square wave inverter would give output something like this, right? And then from this square wave, we need to obtain sinusoidal IS and sinusoidal VL. We need to obtain them in sinusoidal form. So since we have both active series and active shunt compensators, what we will do is these active, both of them will take individual responsibilities. So the who will take the responsibility of making the load voltage as sinusoidal? The series filter will do that. Series filter, active series filter will take the responsibility of making load voltage as sinusoidal, and active shunt filter will take the responsibility of making so supply current as sinusoidal. So they divide the responsibilities in this particular fashion in order to make the both source and load current as sinusoidal in nature. Okay. So let us look at this numerical. We are as a goal, we have to design the filter completely, right? We have to design the shunt and the series part of this filter. So let us first start with the analysis of the source voltage that is given to us. So we know we have already analyzed square wave. So what is square wave? What is the RMS value and everything and fundamental value? All these expressions we know how to derive, right? So in the question, it is given as the load voltage, or the RMS voltage of the load, that is given as 230 volt and 50 hertz, 5 kVA and 0.85 lag, right? This is the about the load. Now we know that we also know that there is a square wave. The source, we know source is a square wave with amplitude 230 volt, plus minus 230 volt, right? This is our source voltage. This is plus 230. This is minus 230. Now we know that the fundamental component of supply voltage for square wave voltage is estimated as, you know, that it's zero point 0.9 times Vs, that is the amplitude, right? So the fundamental component of source voltage, let me call it as Vs1. So the fundamental component source voltage, which we can call it as Vs1, can be written as 0.9 times Vs, and Vs is the peak amplitude of the square wave, which is given as 230 volts. So this thing will come out to be approximately 207 volts. This is the fundamental component value, RMS value of the fundamental component. Okay. Now the load voltage that we have to regulate is given as 230 volt, because our load needs 230 volt. Now we can find out, now we know, let us call the load voltage, which is given as VL. Load voltage that we need to regulate is, let me call it as VL. It is given as 230 volts. Now from that we can say that the AC load current, let me call it as IL, RMS value of AC load current will be given as SL by VL, right? Where SL is the 5 kVA that we are given, the kVA rating of the load, and VL is 230 volts. So 5000 by 230 is given as 21.739 amperes. Okay. Now, if you talk about the A part of the system, that is called as voltage rating of shunt element. It will be equal to the load voltage, which is equal voltage element of the, let me call it as first. Let me call the voltage rating of the shunt element as VFSH, V filter shunt. And this will be equal to the load voltage, which is equal to 230 volt. Now, the second part is calculating the current rating of shunt element. Now, when you talk about the shunt element, we know that it has to take care of two problems. So this element has to take care of two problems. One is it has to take care of the reactive power compensation of the load, and the harmonic compensation. That means it has to supply all the load current that is left after supplying just the active part of the current. So we want that the source current should be sinusoidal. and in phase. That means source should supply only the active component of the load current, and rest of the current should be supplied by the shunt compensator. So shunt compensator will be supplying two currents. First will be first will be this reactive and harmonic current. Now, second component will be due to the fact that we just saw that the fundamental component of our source voltage, that is Vs1, is 207 volts. And we want our load voltage to be 230 volts. Load voltage, we want the voltage across our load for B to be 230 volts. Now, there is a difference in the voltage, right? And we have already seen in UPQCP that whenever there is a difference in this load source voltage and load voltage, there is an active power that is drawn by our compensator, and this active part of the current is also flow will also be supplied using the shunt element. So active part of current. So these two components will be supplied by the shunt element, and therefore these two components will decide the current rating of my compensator. Now, in order to find the value of these two components, the first thing that I need is I need the reactive part of the component, right? So for the first component, let me call it as ISHR. So this component is IL into sine phi, right? Now, I know that so power factor is already given as 0.85. So I know that the load current for my system is given as 21.739. So I can find this IL sine phi as 21.739 into sine phi is under root of 1 minus cos square phi. And cos square phi is given as 0.85. Okay. This component will come out to be approximately 11.452 amperes. Okay. Now, this is the reactive part of the component. Now, second part is the shunt active part of the component. This is given as IS minus IL1A. So that means all the source current that we have to give after compensation minus the active part of current, all that current has to come from the shunt compensator. Now, what is our source current after compensation? In order to calculate this, first we have to calculate the load active power. So load active power is given as PL, which will be equal to SL into power factor, right? 5000 into 0.85, which is given as 4250 watts. Now, after calculating the load active power, we know that the active power component of load, which we call it as IL1, sorry, yeah. So the active part of the active power component of load current, which we call it as IL1A, which is equal to PL by VL or IL cos phi, which is given as 4250 by VL. We know the load voltage is 230 volts. So this will come out to be 18.478 amperes. This is our active part of load current. And after compensation, our supply current will supply only the fundamental part of the load source voltage, right? And we have already calculated the fundamental part of the source voltage as 207 volts. So we can calculate the supply current after compensation. Let me call it as IS. It will be equal to PL by VS1, VS fundamental. Why fundamental? Because since my series filter will take care of the harmonics, so only fundamental component of source voltage will be supplied by the source. So this will come out to be 4250 by 207 volts, which will come out to be 20.531 amperes, right? So so I have got IS, I have got IL1A. So I can calculate ISHA as IS, that is 20.531 minus IL1A, which is 18.478. So this difference will come out to be 2.053 amperes. This is my active part of the shunt current. So I have calculated both active part and reactive part. Now, after obtaining both these parts, so the net current rating of the shunt active power filter will be equal to, let me call it as ISH, which will be equal to under root of I shunt active square plus I shunt reactive square. So both these components will be vectorially added and it will come out to be approximately 11.452 square. So this ISH will come out to be 11.635 amperes. So this was part B, right? So in the part C, we have to calculate the VA rating of shunt element, which will be equal to VFSH into ISH, right? VFSH is 230, we already saw. ISH came out to be 11.635. So the VA rating will come out to be approximately 2675.956 volt amperes. Now, in the D part, now we have to calculate about the series compensator. So we know that the series compensator, how to calculate the voltage rating. We know that the load voltage is, we know that the source voltage is a square wave, and we know that at load side we need a sinusoidal wave. So the difference between the two will be supplied by series filter, right? Series active filter. And we know how to calculate this. We know that VF rating of the series active filter, let me call it as VF series, because we have already used VF shunt. So this VF series rating will be given as the difference of, let us consider over the pi interval of duration. This will be the RMS value of square wave is 230 only, right? So it will be 230, and since it's a sine wave, into sine theta, this RMS, since we are calculating the RMS, we'll calculate the d theta and the square root. So after calculating this parameter, VFSE will come out to be approximately 102.696 volts. So this is the voltage rating for the series element. This is the voltage rating for the series element. Now we know that the current rating of series element will be same as the supply current after compensation, right? And we have already calculated that, which is equal to IS, which is equals to 20.531 amperes. So from that, we can calculate the VA rating of the series element. Let me call it as ISE. This will be given as VFSE into ISE, which is equal to 102.696 into 20.531 amperes. This VA rating will come out to be approximately 2108.458 volt amperes. So the volt ampere rating for the series filter is almost 2 kVA, and for the shunt filter is also approximately 2.5, 2.6 kVA. Okay, so they are almost similar depending on the rating of our system. Okay, so let us move on to the second problem for the day. So in the second problem, we are given that a single phase voltage source inverter with quasi square wave AC output. Now the AC output is not square wave, it's quasi square wave now. Okay, and again the magnitude of this quasi square wave is 230 volts RMS at 50 hertz, and it is feeding a load which is again 230 volt, 50 hertz, 5 kV and 0.85 lagging power factor. The load is still the same, only the supply has changed from square wave to quasi square wave. So again, a single phase UPAC, that is universal active power conditioner, which is consisting of both shunt and series active power filters, is to be designed for this critical load. And we have to calculate the voltage rating of the shunt element and the current rating of the shunt element, the VA rating of the shunt element, and similarly the voltage, current, and VA rating of the series element in order to provide load compensation for unity power factor at AC mains by shunt element and constant regulated sine wave voltage of 230 volts RMS at 50 hertz across the load by series element. The shunt has to take care of reactive power compensation and harmonics, and the series has to take care of the voltage magnitude. Okay. So again, this is the similar circuit. The only difference is that the same square wave inverter is now going to generate quasi square wave. So the inverter, input source inverter, will be called as quasi square wave inverter. Apart from that, everything else will be same. Okay, so I'll just quickly draw the diagram one more time so that you get an idea. So instead of calling this as a square wave inverter, we'll call it as a quasi square wave inverter. So the topology or the physical connections will remain the same, but the control algorithm will change. So it was initially a square wave inverter. Now it is a quasi square wave inverter. Why it is called a quasi square wave inverter? Because it is generating waveform output voltage which is in the shape of a quasi square wave. Therefore, it is called a quasi wave inverter. Okay. Again, there will be a series injection transformer. Then there will be a load. Since it is again 0.85 lag in 5 kVA, the load will be same. Now then there is a series injection transformer. This is a series filter, shared DC link, series interface inductor, and then there is shunt filter. This shunt filter have two connections. One will be like this, another one will be through interface inductor, and it will be connecting through like this, right? This is active filter series, this is active filter shunt, right? Both these filters are present. Now again, this will be ISH, this will be IL, this will be IS, this will be VS, this will be some VDC. Okay, so all these things we have already seen. Now the only difference from the previous case is that the waveform of Vs will be a quasi square wave instead of a square wave. So we know the difference between square and quasi square wave, right? It is zero for certain period of time. So we have to take care of that. So depending on this waveform, the RMS value and the fundamental component value will change. Rest everything will remain same, right? Okay. So we have to again design the series active filter and the shunt active filter as given in the numerical problem. Okay. So let us start by calculating the same things that we have calculated before, only the difference will be in the low source voltage waveform. So again, in this case also the load is a 230 volt 50 hertz load, and 5 kVA is the rating with 0.85 lag power factor. Then in this case, if we are given the the kVA rating of the load and the voltage of the load. So the voltage across the load is 230 volt. From that we can calculate the load RMS current as, let me call it as IL. It will again be 5000 by 230. We already calculated this value in the previous question as well. 21.739 amperes. Okay. Now again in the system also we have to take care of the load reactive power compensation, that will be taken care by the shunt element, and the series filter will take care of the voltage element, right? So let us calculate the value of load active power, which is PL, which is SL into power factor, which is 5000 because it is 5 kVA into 0.85. This will again come out to be 4250, similar to the previous problem. Now we'll again calculate the active power component of load current. Let me call it as IL1A, like in the previous problem. And this is given by PLN VL or IL cos phi, right? So 4250 by 230. This will again come out to be 18.478 amperes. Now, the RMS value of the quasi-square wave, RMS value of supply wave can be calculated as Vs into under root 2 by 3, right? We have already seen the calculation of this. And Vs is given in the question as 230 into under root 2 by 3. This will come out to be, sorry, it will be Vs by under root 2 by 3. So we are calculating the amplitude of the quasi-square wave. This will come out to be 281.691 volts. So this is the peak amplitude of our quasi-square wave. Then the fundamental of the supply voltage. What will be the fundamental RMS value of fundamental component of supply wave? We can call, let me call it as VS1. So this peak amplitude, let me call it as VSDC. And this fundamental is VS1. So this is under root 6 by pi into VSDC. This will come out to be 219.634 volts. Now, from that, we can say that the supply current after compensation, we've already calculated IS similar to this PL by VS1, right? It will supply only the fundamental component of the supply voltage. Therefore, this formula 4250 by 219.634, which will come out to be approximately 19.35 amperes. Now, in the question, we were asked to calculate the voltage rating of shunt element. Let me call it as VFSH. We know that it will be equal to 230 volts because of the load. Next is current rating of shunt element. Similar to the previous problem, it will again have two parts. One is the reactive current, another one is the active current, right? So let me write down the same equations again. So we know that the reactive part of the current is given as IL into sine phi, and IL is, we already calculated, 21.739. Sin phi is under root of 1 minus cos square phi, that is 0.85 square. This value we already calculated as 11.457, right? And similarly, the active part of the shunt is equals to IS minus IL1A. We will subtract only the active part of the component which will be supplied by the source. So I supply current is given as, after compensation, is given as 19.35 ampere, and IL cos phi or IL1A is given as 18.478. So this will come out to be approximately 0.872 amperes. So the net current rating will be of shunt filter. Let me call it as ISH, which is equal to under root of ISH reactive square plus ISH active square, and this value will come out to be 11.49 amperes. Okay. Now the C part will be VA rating of shunt filter, which will be equal to VFSH into ISH, which will be equal to 230 into 11.49, which will be equal to 2642.734 volt amperes. Similarly, we have to do the same analysis for the shunt active power filter. Sorry, series active power filter. The analysis that we did for shunt active power filter, we have to do for the series active power filter. Now we know that in the case of series active power filter, we know that VSDC, we calculated the amplitude of the quasi square wave as 281.691 volts, right? So we know that the voltage rating of series element can be denoted as VFSE, and this VFSE is equal to square root of, we have to take RMS value in three cases. Why three cases? Because quasi square wave can be broken down into three cases. So this is first, this is second, and this is third, right? First, second, and this will be third. So in the first case, it will be just zero. First and third case, it will be zero, the square wave value, but only the the load voltage will be Vm sin theta, right? So if you look at over the pi interval, so this total interval is pi interval. If you look at over this combined interval from 0 to pi by 6, if you look, it will be minus 230, 0 minus 230 root 2 sin theta square d theta. Then from pi by 6 to 5 pi by 6, some magnitude will come, and this peak amplitude is 281.691 minus 230 root 2 sin theta square d theta. Then for the third element, again it is 0 minus 230 root 2 sin theta whole square d theta from 5 pi by 6 to pi. And this value on solving will come out to be, VFSE will come out to be approximately 69.052 volts. Okay. Now, in the next part, we have to calculate the current rating of series element. Let me call it as ISE, which will be equal to the value of supply current after compensation, which we have already calculated, and it is known to us as 19.35 amperes, right? So, using these parameters, we can calculate the VA rating of series element as VFSE into ISE. So VFSE is 69.052 and ISE is the supply current, that is 19.35 amperes, and this will come out to be 1336.161 volt amperes. So this is what we were asked to design, right? So in the second part, if you just compare the rating of these filters, this is 1336 for the series element, and for the shunt element it is 26. So shunt is a higher rated one because of the deformed voltage rating of the quasi square wave. That means when a quasi square, that means one conclusion that we can draw from this is that quasi square wave is better than square wave because the rating of the series compensator for quasi square wave has reduced to 1300 from 2000, right? So that this quasi square wave is better because it has lesser harmonics compared to a square wave. Let us move on to the third problem for the day. So in this third problem, again, we are asked to calculate, we're given a single phase active hybrid filter which is consisting of three branch of passive shunt filter and a series active power filter using a voltage source converter with bus capacitor, And this hybrid filter is designed for critical load of 230 volt 50 hertz single phase thyristor bridge with constant DC current of 20 ampere at 30-degree firing angle. We are asked to calculate the element values of passive shunt filter, the voltage and current and kVA rating of both the series active power filter and the passive shunt filter, which are used in the hybrid filter to provide harmonics and reactive power compensation. So if you draw the diagram of this particular topology, then it would look like something like 230 volt 50 hertz standard sinusoidal power supply is given to this circuit, and then there is a series active power filter and shunt passive filter. In the passive filter, there is a capacitor and an inductor. Let me call it as C3 and L3. Then there is C5 and L5. And then there is a high damp filter, which is LH, RH, and CH. So this is my passive shunt filter. And let me call my load it as, so my load is a thyristor bridge, right? And this thyristor bridge is supplying a constant load. So let me put an inductor and resistor, very high value of inductor, which is taking 20 ampere of constant current at 30-degree firing angle. Now this is a nonlinear load. Now I have to connect a active shunt filter in parallel. Oh, sorry, it's a series filter. So let me draw my series filter as like this: DC bus. Then there is an interface inductor, and I'll connect it to my active series filter like this. So this is my circuit will almost look like this. Okay, this is my active filter which is in series, and then there is a passive filter which is in shunt. So I have to design the series active filter and the passive shunt filter, and this load is my nonlinear load. So my system looks something like this. So whenever you are given a problem, try to first make a diagram so that you get a gist of what your circuit looks like, what will be the rating, and you get most of the half of the problem is solved when you look at the diagram and the waveforms. Okay, so try to start with that. So let us try to calculate the value of these elements. So let us start with what is given in the system. We know it's a 230 volt 50 hertz system, and the load is having a 20 ampere constant DC current with 30-degree firing angle. So since the 20 ampere is the constant DC current for a thyristor load, we know that the AC load RMS current value is, let me denote it by IL, which is equals to the amplitude of the current, constant DC current, that is 20 amperes. We know that is true for a thyristor bridge circuit. We have already gone through this. Then the fundamental RMS input current of the thyristor bridge is given as fundamental RMS input current for the thyristor bridge. Let me call it as I1 thyristor, I1T. This I1T is given as 2 root 2 by pi into IL. So this comes out to be, IL is, we know, 20 amperes. So this comes out to be 0.9 into 20, that is 18 amperes. Now the fundamental active power component of the load, we know it is denoted by IL1A. This IL1A can be calculated as IL1 cos alpha, and IL1 we know it is given as I1T, and cos alpha is given as 30 degree. So this will come out to be 15.588 amperes. Now the fundamental active power of the load, which is denoted by PL, is equals to Vs1 IL1 cos theta, which is equals to Vs1 into IL1A, which is the active power component of the load, which we have already calculated. And Vs1 is directly 230 because it's a sinusoidal wave, pure sinusoidal wave, 15.588. So PL will come out to be 3585.315 watts. Similarly, we can calculate QL because we have to design the passive filter. We have to calculate these things, right? This PL is actually the fundamental component of active power, right? Because we have taken the fundamental component of source voltage, supply voltage, and load current, right? So this is fundamental component of the reactive power. Also, we need this is again Vs1 IL1 into sine theta. So this can be calculated as 230 into 18 into sine theta is 0.5 in our case. This will come out to be 2070 watts. So this is the Q value. Now from this Q value, we know that in order to design, let us first design the passive filter. We know that in the passive filter, there are three branches. One is L3C3, second is L5C5, third is LH, RH, and CH, right? So in the first, first we know that the capacitor, if you assume the capacitances in all the three branches to be identical, so we can directly, we have the formula of capacitor as C is equals to Q fundamental by, let me calculate for third harmonic, N equal to 3 Vs square omega. So this fundamental reactive power we just calculated as 2070, Vs is 230 square, and omega is 2 pi 50. So this will come out to be 41.519 microfarad. So we can say that C3 is equal to C5 is equals to CH will be equal to 41.519 microfarad. So we have find out the value of all the three capacitors. Now let's find out the value of three inductors. So if we look at the third harmonic component, we have already did this exercise, right? L3 is equals to 1 by omega 3 square C3, which will come out to be 27.115 millihenry. Similarly, R3 will come out to be, so Q is equals to X by R. So R is equals to X3 by Q3. And since this is a low pass filter, let me assume Q3 to be 20. So Q3, if I assume 20, X3 is omega 3 L3. So this R3 value will come out to be 1.278 ohms, right? Similarly, for fifth harmonic, if we do the analysis, then L5 will be equal to 1 by omega 5 square C5. Which will come out to be 9.762 millihenry, and R5 will be equal to X5 by Q5, which will be equal to 0.767 ohms. Now let us calculate for the high pass filter or the high order damped filter, which will be used for harmonic order more than 7 and greater than equal to 7. Harmonic order greater than equal to 7. So we will design LH as 1 by omega h square CH, and this H will be 7, right? Because 7 is the minimum harmonic that we need to take care. Omega 7 square CH. So this will give LH as 4.98 millihenry. Similarly, we can calculate the value of RH as XH by QH, and QH for high pass damped filter is in the range of 0.5 to 2. So we are taking 1 in our particular case. This value will come out to be 10.952 ohms. This is 10.952 ohms. Okay. So we have designed all the passive and active components, and now let us calculate the value of the harmonic, these passive filter rating. In order to calculate that, we need to find the value of currents and voltages, right? So we know that I3 will be equal to I1T, that is a fundamental component by 3, right? So it will be 18 by 3, that is 6 amperes. And V3 is equals to I3 into R3, which will give me 7.668 volts. Similarly, we know that I5 is equals to I1t by 5, because we know that in the Fourier series n comes in the denominator, and therefore we are directly dividing the fundamental component by the nth order harmonic. It is 18 by 5, which is 3.6 amperes, and V5 is equals to I5 into R5, which is equals to 2.76 volts. And using that, we can calculate IH, that is the harmonic current that is going to go into the high pass filter, which is equal to under root of I load square minus I1t square minus I3 square minus I5 square. So this current will be equal to 5.2 amperes. Similarly, VH will be equal to IH into RH, which will be equal to 5.2 into 10.952 was the value of RH. This will come out to be 56.950 volts. Now, using these voltage parameters, we can find the voltage rating of series active filter. That is, voltage rating of series active filter can be denoted as V series SAF, VSAF, let me call it as. So V load harmonic, which will be equal to V3 square plus V5 square plus VH square. This will be the sum of all these components. So this will be the voltage rating of the series active filter. So this value will come out to be 57.531 volts. This is our VLH. Similarly, current rating, series active filter will be equal to the supply current after compensation, right? So which is equals to IL1A, which is equals to IL1 into cos theta, which we have already calculated as 15.588 amperes. So the VA rating of series active filter will be equal to V series active filter into IS, or we can give it any name. So when you multiply these two ratings, it will come out to be approximately 896.812 volt amperes. Now let us calculate the. So after calculating the passive shunt compensator values, let us calculate the value of. Yeah, after series active filter, we'll calculate the value of passive shunt compensator. So in order to calculate the rating of passive filters, let me say I want to calculate the voltage rating of passive shunt filter. So it will be equal to VPF will be equal to the V supply square plus V series active filter square. So it will be 230 square plus, because of the connection that is present in the circuit. So this value will come out to be approximately 237.086 volts. Similarly, current rating for this active power filter in shunt can be calculated as, let me call it as ISH. It will be equal to under root of I load square minus IL1A. So apart from the active power component, all the component will be supplied by the shunt passive compensator. This will be under root of 20 square minus 15.588 square. So this will be approximately 12.53 ampere. So based on that, the VA rating of the passive shunt filter will be VPF into ISH, which will come out to be approximately 2970.67 volt amperes. Okay, let us quickly move on to the next question. So in the next question, a single phase UAPC, which is consisting of shunt and series active power filters, is designed for a typical load of 230 volt 50 Hz single phase thyristor bridge with constant DC current of 20 ampere and 60-degree firing angle. If there is a voltage fluctuation of plus 10% and minus 20% in the supply system with base value of 230 volt, calculate the voltage rating of the shunt element, current rating of the shunt element, VA rating of the shunt element, and the voltage, current, and VA rating of the series element. Again, this is a active kind of filter. Here, the only change is that fluctuations are added in the supply voltage. Okay, so the topology will, the diagram will remain same as what we have drawn in the previous question. So we'll directly start with the solution here. Okay, so in this part we are given, let us assume that the per unit voltage variation is X and Vs dash be the, let the per unit supply voltage variation be some quantity X. That plus 10% to minus 20%, let me call it this variation as X per unit. And let me call Vs dash as the point of common coupling voltage under voltage variation condition. So in the question, we will be calculating the parameters under maximum voltage dip, because since we are designing we are going to rate the circuit, right? We have to do the rating. So we will design as per the worst case situation. And from plus 10 and minus 20, since minus 20 is the worst deviation that is going on, that means we'll design for minus 20% deviation. Okay. So let us start with the AC load RMS current. So we know that the AC load RMS current is IL, which is equal to 20 ampere. Again, the same thyristor bridge constant DC current, and the fundamental active component of load of load current will be given as IL1A, which is IL1 cos alpha, which is 0.9 into 20 into cos 60 this time. This value will come out to be 9 ampere. So the active power, fundamental active power that is consumed by the load is given as Vs into IL1A. So Vs, we know it's 230 into 9, which will give us 2070 watts. Now let us say that let us calculate the supply voltage under maximum dip condition. We know that it's minus 20%. So Vs dash under minus 20% case will be Vs into 1 minus X. X is 20. So 230 into 1 minus 20% is 0.2. So 0.8 into 230 will be 184 volts. This is Vs dash. So we'll do the calculations depending on Vs dash. So if I want to calculate the supply current, After compensation, and let me call it as IS dash, it will be equal to PL by VS dash, right? Because my supply voltage minimum amplitude will be 184 volts. It is 2070 by 184, which will be given as 11.25 amperes. Let me call it as IS dash. Now we have to calculate the voltage rating of V rating of shunt element, which will be equal to VFSH, which will be equal to 230 volts, which is given in the question. Now, in order to calculate the current rating of shunt element, we know that it has two components. I shunt reactive component will be equal to I load square minus IL1S square, which will give me 17.86 amperes. Similarly, I shunt active part of current will be IS dash minus IL1A in order to take care of the losses in the or the deviation in the load voltage and the source voltage. Since there is deviation between the two voltages, therefore this current will come into picture, active part of current, and this will flow through our shunt filter. So net current, I'm sorry. So the net shunt current will come out to be ISR square plus ISH A square. This value will be approximately 18 amperes. Similarly, for the series part, if we look at the the VA rating of shunt element will come out to be the product of ISH VFSH into ISH, which will come out to be 4140 volt amperes. Now, if you do the same analysis for the series filter, then since in this particular filter we know that the maximum deviation is under minus 20% case, so the voltage rating of series filter will be corresponding to that maximum deviation. That maximum deviation is Vs into 20%, right? This is 46 volt because 20% of 230 volts is 46 volts. So this will be the rating of our series filter. And we know the current rating of series filter is equals to Is dash, which is equal to 11.25 amperes. So from this, we know that the volt ampere rating of series is equals to VFSE into ISC. This is ISC. This quantity will come out to be 517.5 volt amperes. So this was pretty simple, right? The only change in this was the voltage deviations. So how to take care of the voltage fluctuation that came into picture, right? So let us move on to the next problem. So in the next problem, it is given that this is a problem for three-phase system where a quasi square wave AC output is present and the line voltage is 400 volts at 50 hertz and there's a critical load with 415 volts 50 hertz and this load has a kVA rating of 40 volt and 0.85 lagging power factor. So a three-phase UPAC has to be designed, which is a combination of both active shunt and series filter. And again, we have to find the voltage, current, and VA ratings of both the shunt and series elements. So this particular filter will look exactly similar to the single phase, only the modification will be the three phase. And here both since both the components are active, the converter would look almost the same, right? So let us directly start with the design of this filter. So in this case, we know that the load line voltage is given. So from the line voltage, we can calculate the load phase voltage. Let me call it as VLP, P for phase. So this will be 400 by root 3, which will come out to be approximately 239.6 volts. So this is 415 volts. Okay, so this is the desired load phase voltage. And the magnitude of DC side voltage of the supply side is estimated as magnitude of DC side voltage of supply side voltage source inverter is estimated, let me call it as VSDC. We've already used this variable, and this is VSL by under root 2 by 3. We have used this formula as well, and this will come out to be approximately 489.89 volts. So the load current can be calculated, the load line current IL is equals to, since it is 40 kVA by 3 into phase voltage 239.6. The load line current will be 55.648 amperes. And the active part of load current, let me directly write it as IL1A. Active part of load current is equals to SL into PS, that will be active power, divided by 3 into VLP, load phase voltage. So this will be 40,000 into 0.85 by 3 into 239.6. This will come out to be 47.301 amperes. And the fundamental component of the supply side load voltage, that let me call it as VSL1 is equals to root 6 into VSDC by pi, which will be given as 381.972 volts. The same procedure, but only the equations will be changed. So the fundamental component of the supply fade voltage. So we just calculated the supply line voltage fundamental component. So voltage component of the fundamental supply current is equals to VSL1 by root 3, which will be 220.532 volts. So the supply current after compensation can be calculated as SL into power factor by 3 into VSP1 corresponding to fundamental component, because only the fundamental component will be supplied by the voltage source. The reactive power component will not be supplied. Now let us move on to the rating calculations. If you look at the voltage rating of shunt element, let me directly write it as VSH. Voltage rating of shunt element will be equal to the load voltage, which is equals to 239.6 per phase in our case. And then current rating of shunt element, if we want to calculate, we have two components, right? ISHR, that is under root of IL square minus IL1A square, which will be equal to 29.315 amperes. Similarly, ISH active component will be IS minus IL1A, which will be equal to 4.09 amperes. So ISH will be equal to under root of ISHR square plus ISHA square. This component will come out to be 29.599 amperes. So from this we can calculate the VA rating of shunt filter as VSH into ISH, which will be equal to 21.276 kVA. Now for the series filter, if we look at, so if we look at the D part, we know that it will be a stepped waveform, right? We have already looked at the stepped waveform with magnitude VD by 3 to VD by 3, right? VD by 3 to VD by 3 and VD by 3 again for the interval of equal intervals, right? For equal interval of 60 degrees. So using that, we can calculate the voltage rating of the series filter as we've already used this kind of equations before. From 0 to pi by 3, it will be 239.6 root 2 into sine theta minus VD by 3 is 163.29 square d theta plus pi by 3 to 2 pi by 3 will be 239.6 root 2 sine theta minus 2 Vd by 3 will be 326.59. And the third element will be 2 pi by 3 to pi. Again 239.6 root 2 into sine theta minus again Vd by 3, that is 163.29 whole square d theta. This after solution this will come out to be approximately 71.15 volts, and we know that the series current will be equal to the supply current after compensation, and we had just calculated supply current after compensation and it came out to be 51.391 amperes. So the VA rating of series compensator will be VFSC into ISC, and this will come out to be 10.969 kVA. So this was our last question for today. In case you have any doubts, then please feel free to ask.
Madam,
Yes, sir.
madam, at least you have to take one session on MATLAB, madam. MATLAB simulation results. Yes, my person.
MATLAB simulation results. Okay. I could have taken it, but since this content, I don't have extra lectures. I have only 12 lectures. And if I take something else, then I will not be able to cover what is there to cover.
Now, 10 completed, madam. Remaining two sessions are there, madam.
Yes, only so in the 2 sessions, I have to take off the remaining lectures, right? That is the minimum I have to cover.
One is this is the last. If you completed 10 weeks, madam, but hereby you submitted 11 assignments, madam.
Uh, yes, so what happens is
One more
in the
session is it is possible you have to take, madam. Yeah.
actually we are like assigned only that much. We cannot take more. It is coming like it the assignment of these lectures come from NPTEL. So we cannot do that right now. But I'll check if it is possible.
Okay, okay, madam. Okay.
Okay. Okay, then we'll end today's session.
Thank you, madam.
Okay, thank you, sir.